Okay, question 7 was Sean on a bike ride. She started at 2 o'clock, 1400 hours, and then it's got the velocity time graph, okay? So it says then, during which quarter of an hour period was Sean's acceleration the greatest? Okay, now, in terms of the acceleration, you get the acceleration from the gradient, okay? So sometimes we have to draw a tangent to work out the gradient, and we get the acceleration. But in this case, they're not asking for the acceleration, they just want to know when it's at its greatest. So we're going to look at when the gradient is at its steepest, where it's steepest. And you can see here that this is where it's steepest here. I mean, here it's not so steep, isn't it? And it's starting to get steep, and then it's steep during this quarter of an hour period between 14:30, that is, isn't it? And 14:45. Okay, that's when it's at its steepest. Of course, it's still quite steep then, but it's getting less steep, okay, as you go along. Now, you might look down here and think, blinking heck, you know, this is quite steep here as well, but this is when the velocity is actually decreasing. If you look at her velocity now, it's actually, she's slowing down actually, right? She's slowing down and it's going to 0. So she's not actually accelerating there. She's not accelerating because she's slowing down. She's doing something called decelerating, okay? So decelerating is kind of like the opposite of accelerating. Whereas accelerate, you speed up. Decelerate, you speed down. So we'd ignore this. It's only when we've got positive gradient here. This is what we're interested in. And this is where it's at its steepest. Okay. At about what time did Sean stop accelerating? Now remember what I said earlier about acceleration, it's all about the gradient of here. If she stopped accelerating, that means the acceleration, A, we call it, is 0. That means the gradient is 0. So we're looking for flat, okay, when the curve is flat. So the gradient is 0. If you look up here, I could even draw in at the top. It's interesting, isn't it? Because at the top is where it's flat, the gradient. If I draw a tangent there at the top, okay, because it's flat, she's peaked. Right? That's where she stopped accelerating. I mean, ultimately, what's happening is her speed is no longer increasing, and it's not actually decreasing as well. She's going at the same speed. So going at the same speed means she's no longer accelerating. So, yeah, around there. So we can see, maybe we'll go for that time there. That would be accepted, 15:15. Okay, the time there, or slightly before as well. They'd accept that there. If you took in a time in that range as well, that would be accepted. Okay, so next part then. Sean usually finds cycling at a velocity of 18 kilometers very comfortable. Express this in meters per second. So 18 kilometers per hour, change it to meters per second. Now we don't need the graph for this, but what we do need is to sort of think about scaling here. So 18 kilometers. Now remember, 1 kilometer is 1,000 meters. So 18 kilometers per hour would be 18,000 meters. Now, what I do is I sort of write it like this, 18,000 kilometers, or 18 kilometers in 1 hour. That's what that is, isn't it? 18 kilometers per hour. It's 18 kilometers in 1 hour. I'm going to change that to meters. So 1,000 meters is a kilometer, so that'll be 18,000 meters in 1 hour. And I'm going to scale it. I need to scale it down, don't I? I need to make this time period a lot smaller. We need to get to a second. So let's go down in stages. Let's go down to say 10 minutes to start with. Okay, so to get from an hour to 10 minutes, I've got to divide by 6, haven't I? Yeah, because there's 6 10-minute intervals in an hour. Okay, so then obviously then if I divide that by 6, I need to divide the distance by 6. And 18 divided by 6 is 3, so it'll be 3,000 meters in 10 minutes. Now 10 minutes we get in there, but we need to get to a second. Let's just take our time and let's go down now. Let's divide this by 10 so we work out what it is in 1 minute. So divide this by 10, you get 300 of course. 300 meters in 1 minute. Now, you're close on me. 1 minute is 60 seconds. Yeah, so to get to 1 second we need to divide by 60. So we get 1 second. We need to divide the distance by 60 then, and 300 divided by 60 is just 5. So 5 meters in 1 second. So we can say 5 meters per second is our speed. Okay, so question D, part D. It says, using her velocities at 1400, 1500 and 1600, calculate an estimate for the total distance she travelled between these times. Okay. Now, when it comes to that, we need to use the graph, and we need to recognize the distance. We need to remember distance is just the area. Okay, so the area under the curve on the velocity time graph gives you the distance. And it says at these times, doesn't it? 1400, 1500. Let's draw a line here. 1600, and that's it. We're only interested in these two sections here. Okay, we're not interested in this one because it does say in the question, doesn't it? Between 1400 and 1600. Okay, and it says look at those velocities there, 1400, 1500, 1600. So if I call this area 1 and area 2, and if I form here a trapezium, and a trapezium here as well, okay, or actually it's a triangle, isn't it, really, but we can think of it as a trapezium. So we've got a trapezium, two trapeziums, and we work out individually now the areas. So area 1 will be, so as I said, you can use it, think of it as a triangle if you want, or the trapezium formula, which is on page 2. So the two sides that are parallel are these heights here, these lines to the curve. So what's parallel here is this line, which is 0, it doesn't exist, okay, right? And you've got this line then, which is of height, I think that comes out to be 18, okay? So that's your A and your B, and then you times it by the distance between them, which is just 1 hour, so that's 1, so that comes out to be 9, because half of 18 is 9. Area 2, half A plus B, well your A is 18, we established that before, your B is that there, which is 14, times by the hour between them, that height between them, which is 1, and that comes out then to be, well, half, 32 in the bracket, times 1, so that's 16. Add them together, so you get 25 kilometres, okay, that's the area, gives you the distance. Part E then, it says, Sian estimated the distance she travelled between 1600 and 1700 as 5 miles. Is Sian's estimate reasonable? Well, you must justify your answer. So between 1600 and 1700, well, we've got to work out the area of this now then. Okay, so I join that up. Now, there, you join those two up. Again, it creates a triangle. There's quite a bit here, not covered actually. Quite a bit not covered. So if we work out the area here, okay, so area between 1600 and 1700, and I'm being careful here just to explain what I'm doing because it is one of those communication questions, so underline that maybe. So that will be area will equal half, again you can use the trapezium rule, half times A, which was 14, wasn't it? That height there was 14, plus 0 times 1, so that comes out to be 7 kilometres. Okay, now 5 miles is what she estimated it to be. The estimation, again I'm just annotating my way through explaining what I'm doing, so 5 miles. Now you need to know that 5 miles is actually 8 kilometres, okay, approximately, okay, 8 kilometres. Maybe put a squiggly line there to show it's approximately equal to 8 kilometres. That's something you need to remember. Well, yeah, that is reasonable, isn't it? Is this as reasonable? Well, yes, probably. She's estimating 8 miles, which is 8 kilometres, and we've worked it out to be 7 kilometres. So her estimate's slightly more than our. So we can say that her estimate is slightly more than our area calculation. Okay, but then again, our area calculation didn't take account for all of the area under there, so it would make sense, wouldn't it? Yeah. So, however, our area didn't account for all area under the curve, so that 8 kilometres is sensible estimate. Okay.